Okay, well, last time we talked about the approach, we basically outlined the computations used in order to calculate the apparent conductivity that's measured at the surface. In this case, over a three-layer model. Remember, we had three weighting terms. The apparent conductivity that we measure is just a linear combination of the conductivities, linear sum of the conductivities of each of the layers in the subsurface. And the weights are related to the cumulative response function. And you have 1 minus R1 minus R2, and R2. And so again, this is just a weighted sum of the individual conductivities. This R1 minus R2, as we noted, is just allows us to get this area between Z1 and Z2. We'll talk a little bit more about those, what the R's are and how we get them in a few minutes. But this is the basic equation that we used in the previous example, and the equation that you would use for any. We use different conductivities, but the equation that you'd use for any three-layer problem. And in this case, we have a setup similar to what we worked the last time. So the relative response function, defines how the instrument responds to conductive layers at varying depths or at varying values of Z, where Z is D over S. So Z obviously varies, a Z equal to 1 would be 3.67 meters for the EM31. It would be 10 meters for the EM34 with a 10 meter intercroll spacing. So these Z's, are related to depths, but depends on what the intercroll spacing is. And you can see we're going to talk mostly about the, we're going to be assuming a vertical dipole orientation, so we'll be working with this curve here. But just to show both functions, notice that the relative response function for the horizontal dipole is really, we get kind of a very high contribution of relatively high contribution of the conductivities of the near surface layer compared to those at depth. The relative response function for the vertical dipole parallels, once you get out past about a Z of 0.5, they're roughly parallel to each other. The relative response for the vertical dipole is a little bit greater than that for the horizontal dipole. But there's a real divergence here as we get into the near surface. And these are just the formula that one would use in order to calculate the relative response function for the vertical dipole and the horizontal dipole. Remember that R is an integral of this, so we end up getting 1 over 4z squared plus 1 to the 1/2 power for our R. And what I've done here is I've just taken the relative response function for the vertical, and I've highlighted it for the vertical dipole, and I've just illustrated that each of these layers, sigma 1 with conductivity sigma 1, sigma 2, and sigma 3, which is equal to sigma 1, contribute to the apparent conductivity in proportion to this area under the curve, which I've kind of highlighted and colored here. So the first layer with a conductivity of 20 millisiemens per meter in this case contributes to the apparent conductivity in proportion to this area, which is 1 minus R1. The second layer in proportion to R1 minus R2, which gives us this area. We'll talk a little bit more about that later. And the third layer contributes in proportion to the remaining area out to infinity. So that's your 1 minus R1. This is your R1 minus R2. And this is your R2, this area under the curve. So looking at, just an individual point, we really get no contribution. If we have a really thin layer, the contribution is in proportion to the area under the curve. And so if we're just looking at a single depth, we don't really get any contribution from something which is infinitesimally thin in this case. So we have to have a significant delta z. Otherwise, the contribution goes to 0. So very thin layers really don't contribute to the apparent conductivity. So as the thickness of the layer increases, then we begin to see some influence, some the presence of this layer is apparent in the apparent conductivity that's measured in the surface. So, and its contribution would be proportional to this area under the curve between Z2 and Z1. So we just have a Z1 and a Z2 there, and the contribution to the apparent conductivity measured at the surface associated with this layer would just be proportional to the area under this curve. Remember, that's R1 minus R2. If we take a look at a homogeneous half space that has a constant conductivity, well, no calculation necessary perhaps, but we kind of intuitively would expect that the apparent conductivity must be equal to the conductivity of this layer. And so we'd have a formula where we have that sigma A is equal to sigma 1 times the total area under the curve, which is equal to 1. So sigma A would just be equal to sigma 1 times 1 minus R1, but R1 in this case is 0, because there isn't a second layer, so we just get sigma A equal to sigma 1. And as we mentioned the last time, when we were dealing with the 3-layer problem, we have apparent conductivities measured at the surface. The conductivities of each of these 3 layers are going to contribute to the apparent conductivity in proportion to the area under the relative response function. A little redundancy here, but just to illustrate the idea. Layer 1 with conductivity sigma 1 will contribute in proportion to this area, which was 1 minus R1. Layer 2 in proportion to R1 minus R2, and layer 3 in proportion to R3, which would be the remaining area under the curve. So the area could be easily calculated as Z1 to Z2, the integral of Z1 to Z2 of phi v of z dz. And that would be one way to do it, and that would work. It's a little bit more cumbersome. What McNeil has done for us is develop an approach where we use the cumulative response function, and again, we're in the problems that we're going to look at, we're going to be assuming a vertical dipole orientation. So RV of z is just 1 over 4z squared plus 1 to the 1/2 power. And we're going to be using these RV of z's in order to calculate these areas. And, so for the next time, just continue your reading and develop a general appreciation of the relative response function, the cumulative response function, and think about how we can use these cumulative response functions in order to calculate this area under the relative response function. More next time.